theorems that would give us more tools. Okay. Okay, so that's what I'm going to do. So I'm going to write down some theorems, and then as we write the theorem, then we're going to be doing examples to see how these theorems can be used. Okay. For example, here is a very important theorem that we have been using implicitly, but it's time to write it down. Now, this class, we don't have the knowledge to be able to prove this theorem. Okay, so we'll be able to prove this theorem. However, it's an important fact that we need to use. Okay, so to prove this theorem, you need to know complex analysis. Anyways, this is called the fundamental theorem of algebra. And basically what it says is that if you're looking for zeros of a polynomial, you're going to find them. Okay? Because this theorem is the one that tells us that every polynomial of degree at least 1 is going to have at least one complex zero. Okay? So every polynomial will have at least one zero. Of course, the degree has to be at least 1, otherwise it's a constant polynomial, and other than the zero polynomial, then it's not going to have zeros, but those cases are not interesting. We are interested in polynomials of degree 1 or more. Anyways, that's what the fundamental theorem of algebra says. It's only telling us that every polynomial with complex coefficients of degree at least 1 has at least one complex zero, meaning if you're given a polynomial and you're looking for zeros, you're going to find it. That's all it's telling you. Okay, there are zeros. Now, whether you can find them or not, that's a different story. They are there, but if you can find them, that's another thing. For example, let us use this polynomial and this theorem and our knowledge from the factor and remainder theorem to answer this question. So this question says, here is our friend, the one that was very hard for us, show that this polynomial has 3 zeros. Of course, one way to answer this question would be to just find the 3 zeros, but as we know, this is out of reach right now. But the question is not asking you to find the 3 zeros. It's asking you to show that this has 3 zeros. That's a different story. Okay? So how can we do that? Well, we can do this very nicely. So solution. So, you know, we need to do a little proof. So why is it? Let's convince ourselves that this polynomial has 3 zeros. Well, first of all, by the fundamental theorem of algebra, we know that it's going to have a zero, right? So by the fundamental theorem of algebra, I'm going to abbreviate this as FTA. By fundamental theorem of algebra, F has at least 1 zero. Of course, it could be a complex zero, but that's okay. Okay, has at least 1 zero. So let's call it. So say this zero is x equals c1. Okay. So then, by the factor theorem, using the factor theorem, it means that x minus c1 is a factor of f. So far we know that f of x has a form x minus c1 times some polynomial. So let's call it q of x, okay? Where the degree of q of x, when you do division, right? Where the degree of q equals, who can tell me what's the degree of this q? What's the degree of this polynomial? Are you sure? Remember, q here is a quotient. So polynomial f has degree 3. We took out x minus 1 as a factor because x minus c1 as a factor. And what's the result? Is a polynomial of degree 2. Good. Remember, the overall sum has to be 3. Degree of f is 3. The sum of these 2 degrees, it has to be 3. So 1 plus 2. Okay? All right, so now the degree of q is 2, which is at least 1. So it's greater than or equal than 1. So what does that mean? We can now use fundamental theorem of algebra again. Can you repeat that, please? Okay. Well, all I'm saying is that f has degree 3. Yes? F has degree 3. Therefore, in this equality, the left-hand side has degree 3. So whatever we have here, the total degree has to be 3, right? The total degree has to be 3. So we already know that one of the factors is degree 1. That's x minus c1. So if the total degree is 3 and one of the factors is 1, as it has degree 1, what's the degree of the other factor? It has to be 2, right? Because when you multiply polynomials, you add the degrees. All right, good. So the degree of Q is 2, and because it's at least 1, we can now use fundamental theorem of calculus again. So using fundamental, of algebra. There is also a theorem called fundamental theorem of calculus, but as you can imagine, that is for calculus. But that's a different story, has nothing to do with this. Okay, so fundamental theorem of algebra then gives that Q of X has also a 0, okay? It has a 0. It could be the same as the original one that we found for F, maybe it's a different one, so I'm just gonna call it C2. Say C2. So by the factor theorem, we can factor out Q of X as X minus C2 times, let's call it H of X, where here the degree of H is 1, because remember, Q had degree 2, okay? So that means so far that f of x has the form x minus c1 times x minus c2 times this mysterious h, but this h is really not that mysterious. It's a linear polynomial, so it has a form ax plus b, right? Where a and b, remember, they are complex numbers, because this is using these c's, they could be complex numbers, they don't have to be real. That's what fundamental theorem of algebra says. You need to allow yourself complex solutions, otherwise just consider this polynomial, okay? X squared plus 1. There are no real solutions here. All the solutions here are complex. So this theorem makes sense if you talk about complex numbers in general. But the point is that H has degree 1, so it also has, again, fundamental theorem of algebra implies that H has a 0, say C3. So f of x can be written as x minus c1, x minus c2, and then H would be x minus c3 times something, but that something is just a number because it has to be 1 degree less, and because H had degree 1, this is just a coefficient, which is degree 0, okay? So that's H. In other words, the H here is x minus c3 times A. Now, what do we know about A? Notice that if you multiply all of this is equal to ax cubed plus lower degree, guys, and our polynomial is x cubed. This is supposed to be the same as x cubed plus x plus 1, right? That was our original polynomial. From here, we can conclude that a must be 1, because the leading coefficient here must match the leading coefficient here. So anyways, that's how we can show that this polynomial, even if we don't see them, has 3 zeros, okay? So that's how you can use fundamental theorem of algebra to convince yourself that a given polynomial is going to have, and then this is the first corollary that we're going to see, and as you can see, it follows immediately from fundamental theorem of algebra. It's not just that it has 1 zero, it's going to have as many zeros as the degree of the polynomial. Once again, this is something that you have been seeing in the homework and in the videos, but here is a formality of why that's true. As you saw here, this is a degree 3 polynomial, and we just proved that it has 3 zeros using fundamental theorem of algebra. You can imagine that if you had a degree 20, you just keep on doing this process 20 times, and you will find yourself 20 zeros. Now, of course, these zeros, they could be repeated. They could be the same. And we never said these C1, C2, and C3 are unique. They could be equal. So that's where multiplicity comes into play, okay? So anyways, this shows then that x cubed plus x plus 1 actually has 3 zeros, and moreover, we just also show that we can factor it as a product of linear factors, okay? And that's what you're seeing right here. And that's actually the corollary that we have in here. Actually says it's called the linear factorization theorem, which tells you that any polynomial of any degree, as long as it's 1 or bigger, can always be factored as a product of linear factors, where of course you're going to have complex numbers as coefficients, and the zeros are not necessarily unique, okay? So there could be some repetition. But how do you justify this linear factorization theorem? Exactly the same way that we did here. Just consistently begin applying fundamental theorem of algebra, taking one factor at a time and reducing the degree until you get down to n factors. And okay, let me just say the other statement and then I ask you for questions. And then, something that follows immediately from that is the number of zeros of a polynomial. That it's not just that every polynomial has at least one, no, it has exactly n zeros, where n is the degree, if you count those zeros with multiplicities, of course. For example, look at the previous example that we just did. We had a degree 4 polynomial, but we only found 3 zeros. But yes, one of them was appearing twice, right? Because it had multiplicity 2. So really, when you add the multiplicities of all your zeros, that has to be equal to the degree of the polynomial, okay? If all are different, then that means every zero will have multiplicity 1. But you may have higher multiplicities, and then that is reflected, in the degree. You only have 3 zeros and the degree is 4, then there has to be one with multiplicity at least 2, okay? That kind of stuff. All right. Anyways, these two corollaries, they are direct consequences of the fundamental theorem of algebra. The factorization theorem that guarantees that you can always factor over the complex numbers. You need to consider complex numbers. And also the number of zeros, that you know that every polynomial will have as many zeros as its degree. And this is counting multiplicity and keeping in mind that they could be complex. All right, questions about the treatments that we discussed. They are fundamental theorem of algebra, linear factorization theorem, and the number of zeros. Do you have questions on this? Yes. In fact, Emily, we have been using linear factorization theorem all along. Look, you want to see examples? Here are 2 examples. Remember, those theorems are just theorems about existence. That theorem is just telling you, hey, you can do this. You have a polynomial, you can factor it as a product of linear. The theorem is never telling you how you do it. That's a different story. But for example, here you have 2 examples in which we successfully did it. We started with this cubic. There you go. Look at this line right here. We factor it as a product of 3 linear factors. And therefore, you can see that there are 3 zeros. And another example. We started here with a degree 4 polynomial, and then along our process, what do we do at the end? Look at this line right here. We factor it as a product of 4 linear factors, and remember, we never said that they have to be distinct. Here we see a repetition, because one of the zeros was appearing twice, but that's okay. All right, we're going to do more examples now, but that's all the theorem is telling you, is that this is theorem about existence. Because why? I mean, we care about this in mathematics, because when you want to look for something, like in our case, we're looking for zeros. You want to make sure that there is something to be found. You don't want to go to a place and look for something if you have no idea whether what you're looking for is there or not, okay? These theorems are here to tell us, okay, whatever polynomial in front of you is going to have zeros. Now, whether you can find them, that's a different story. But it tells you they are there. Your job is to find them, but they are there. So there is something to be found. I don't know if you understand the difference, okay? So these are existence theorems. So they don't tell you how to do it. They just tell you, okay, this can be done. That's all they're telling you, okay? But they don't tell you how to do it. So that's, okay. Anyways, but we're gonna keep doing more examples, but all the examples we have done so far, they are examples of the linear factorization theorem, because as you can see, we are always factoring. And then at the end of the day, we always write down a polynomial completely factored. And that's what the linear factorization theorem says, that you can always manage to do this. Okay? And I want you to pay attention to this right here. Notice that you have your product of linear factors, and then you have a number here by itself, which is an, and that is the leading coefficient. Because of course, if you multiply only these factors, you will have x to the n plus lower guys, okay? So if the polynomial has a leading coefficient, you have to, distribute it over, and the point is that that leading coefficient is going to show up at the beginning. So this is helpful. And you have been using this implicitly when you have been doing your homework. That they give you a picture and you have to find a formula, then you have been using this implicitly when you figure out the equation of f. Okay, anyways, so that's that. So let's see. Let's use let's do some examples of how else you could use this. Okay. Before I do that, let me give you another theorem. So instead of let me use Roman numerals here. So I, y, and then here this will be number 2. So we had the fundamental theorem of algebra above. Now here this another theorem is called the conjugate theorem. Okay. And you have seen this for quadratic equations. As you know, if you have a quadratic polynomial, and if it has a complex 0, actually that complex 0 comes with another one. It comes with its conjugate, right? Because when you look at the quadratic equation, there is this plus or minus business. And if you get a complex solution, it's because your discriminant is negative, and therefore you're going to have a complex number and its conjugate. So 2 complex solutions. And this is for quadratic polynomials. The point is that this is always true in general, okay? If a polynomial has a complex number as a 0, then the conjugate of this complex number also is a 0 of the polynomial. In other words, complex numbers, they come in pairs, okay? So another way of saying this is that every polynomial can only have an even amount of complex zeros, okay? So that means when you pair this with what we said above about the degree, that we're going to have as many zeros as the degree. If you have an odd degree polynomial, you have to have at least one real 0. Okay? Just because you can only have an even amount of 0. So you have a degree 7 polynomial, you can only have up to 6 complex zeros. So there has to be at least one 0 that is real. You can also argue with the end behavior and the intermediate value theorem, because odd degree means that you start at quadrant 1 and finish at quadrant 3 and finish in quadrant 1, or the other way around. Start at quadrant 2 and finish in quadrant 4. Any of the 2 choices, you will always go to the x-axis. It's one way to argue. Another more sophisticated way is doing this argument that I'm telling you now, by looking at the number of zeros and the type of zeros that you're allowed to have. But even degrees, they may have no real zeros at all. Like you could have a polynomial like this, like the one that I just drew. Okay, the degree of this is at least 4 because we have 3 turning points, right? And for the looks of it, there is no real zeros here. So all the zeros of this polynomial that I just drew, they're going to be complex numbers. So this we have at least 4 complex zeros. Okay, but we know they come in pair. So a complex 0 and its conjugate, and then another complex 0 and its conjugate. All right, so that's all information that this theorem is telling us. And if you want to prove this, let me actually give you the hint. So the proof of this theorem, I would like you to try it on your own. If you have questions, then you can, come to office hours, and then I'll gladly explain. But it's not hard. It's simple. All you really have to do is prove the following. So use the following property. So show that, so to convince yourself of this, show the following things. First, show that if you have a complex number, okay, you look at its conjugate, and then we raise it to the n power. These 2 operations are commutative. In other words, you first do the n power of the complex number, and then you take its conjugate. All right. And to give you a more clear hint, this clearly follows from the following simple property, that if you look at a product of 2 complex numbers and then you take the conjugate, this is the same thing as first taking the conjugate and then multiply. Okay? So this property of the product can be extended to this power with integers. And then another point that you will need to convince yourself is that when you add 2 complex numbers and you take the conjugate, that's the same thing as adding the conjugates by themselves. So it distributes over addition. So basically, this follows from the fact that the operation of conjugate distributes over addition and multiplication, okay, when it comes to complex numbers. So verify these two properties, and then once you have properties, once you're convinced of this, then you can easily argue the theorem that is in front of you. Okay? Because if C is a zero, if a complex number is a zero, when you plug it into a polynomial, you can keep on using these properties, and then you will find that the conjugate must be a zero as well. Okay? So think about it if you want. This is, FYI, and if you want to ask me questions about it, you can do so during my office hours. But I want you to think about it first. See if you can write down some convincing argument. Okay, anyways, what I want you to take home with you and that you're going to be using in practice is this: the fact that if you know that a complex number is a zero, then its conjugate is also a zero. Okay, so being given a complex number as a zero, you get for free another one, which is its conjugate. Do you understand this? All right, so let us do one example on that. Okay, then I'm going to come back and give you more theorems. Actually, one more theorem. But before I do that, let us use an application of factor theorem and this conjugate business and so on. All right, so given that the polynomial f of x equals, let's do another degree 4, 6x cubed plus 5x squared plus 30x minus 50. So given this polynomial, and now I'm going to give you, okay, I'm going to give you a head start. I'm going to give you that 3 minus I is a 0. And the 3 minus I is a 0. Okay, with this information, find all the zeros. So find all the zeros of f, and in fact, we're going to factor f completely, right? Finding the zeros means to factor f completely as a product of linear, as a product of factors, as a product of linear factors. Okay, so let's see. So we are given that 3 minus I is a 0. That's good. What else do we get for free then? Who can tell me? According to what we just discussed, we know we're expecting 4 zeros, right? Because the degree is 4. We already have one, 3 minus I. What else do we get for free? Which one is it? Okay, good. 3 plus I, very good. Given that 3 minus I is a 0, 3 minus I is a 0, and so then we get for free that 3 plus I is also a 0. Everybody okay with this? So that means that f of x, keep the same color. So from here it follows that f of x is going to be equal to x minus 3 minus I, x minus 3 plus I, right? This is using my factor theorem, and then times some polynomial. Let's call it q of x. Are we good so far? All right. Now here is another little fact. Whenever you have a complex zero and its conjugate, that will give you these two factors that we wrote here, right, with the complex numbers. Actually, when you multiply these factors, then the I is going to be gone. Okay, so you can actually convince of this on your own. So I'm going to show you here, but the I is going to be gone. So to figure out what Q is, and by the way, before we do that, can anybody tell me what's the degree of Q? So what's the degree of Q? Remember, when you're doing problems, you need to see the light at the end of the tunnel. So the degree of the Q is 2. What does that mean? It means that once we figure out Q, we're basically done, right? Because remember, if you get degree 2, once you figure out what Q is, then you're basically done, because degree 2, you can use the formula if you need. All right? So we're basically done with this. All right, anyways, to figure out Q, what we're going to do is the following. Let's multiply the two polynomials that we have, the two factors that we have with the complex numbers, to get something with real coefficients. And then basically what we're going to do is division. We divide f by that, and the quotient, we know it's going to be an exact division without remainder, and the quotient has to be Q. Okay, that's a strategy. All right, so to multiply this, let me go ahead and do it here. So I'm going to multiply these two factors. So I'm going to rewrite this a little bit. So I'm going to write this as x minus 3, I'm going to put that in parentheses, plus I, and then the other is minus 3, I'm going to put that in parentheses, minus I. So I distribute the negative in the second one, and well, in both of them. And the reason why I did it like that is because now notice that what we have here is a difference of squares, right? We have here something that looks like a plus b, a minus b. You could FOIL and do all of that, but I'm doing this so that we can do it quicker. So this is going to be the first guy square minus the second guy square. And notice how the I now is gone. And the point is that you can always play this game. That's why I'm saying that whenever a complex is a zero and it's conjugate, you can multiply those two factors and the I is gone and you get real coefficients. After all, the original question had real coefficients, so there should be no I left over if we multiply. All right, so what is this? So we're gonna have x squared minus 6x plus 9 and then plus 1 because I squared is negative 1 with the minus becomes positive 1. So this becomes x squared minus 6x plus 10. Okay, so let's write down f of x. So f of x equals x squared minus 6x plus 10 times something. That's what we know. And now our job is to figure out q. How do we find q? Well, we're going to do division. Now, in this case, synthetic division doesn't work because the degree, we're dividing by something of degree 2. So here is where we need long division. That's why we took some time last week to remind you of this, because sometimes we need long division. Okay? So now we find q. So we find q by using long division. All right, so let's go ahead and without further ado, and let's do that. So let's see, are there any questions up to here? Are you following? Do you understand what's going on? Anybody wants to ask any question up to this point? Okay, so I'll continue then. All right, so I'm gonna begin the process, okay? So x squared, so that would be x to the 4 minus 6x cubed plus 10x squared. We subtract, and what do we get? These guys cancel, and so we're gonna have, okay, these guys cancel as well. It's nice. So we have 15x squared, no, negative 5. Negative 5x squared plus 30x minus 50. The degree is the same, so we continue. So we put the minus 5 here. So we get negative 5x squared plus 30x minus 50. Remember, we know that we're going to get 0 because we know that x squared minus 6x plus 10 is a factor, okay? In fact, by doing this, we are now making sure that we did not make a mistake, okay? But why did we do this? Because now this guy right here is our q, right? That's a quotient. So this right here is our q of x. So f of x equals x squared minus 6x plus 10 times x squared minus 5. And now we can immediately see that the other two zeros that we're missing are plus or minus square root 5, right? So we get x squared minus 6x plus 10 times x plus square root of 5, x minus square root of 5. So what are the zeros of this polynomial? So the zeros are 3 minus I, 3 plus I, negative square root of 5, and positive square root of 5. And they all have multiplicity 1. So all with multiplicity 1. Okay, questions? Questions on this? Okay. All right. So that was that example. So let's see. I guess let me do another one that you may find, or you may have been finding in the homework. You should know how to do that. So let's see. Find the third degree polynomial. Sometimes this means a degree 3 polynomial. Find a third degree polynomial f of x with integer coefficients and with zeros. So the coefficient has to be integers, and then the zeros have to be, and then I'm telling you the zeros. With zeros 2 plus I and 4 over 3. This is another type of problem that you could encounter. Okay. So how do we answer a question like this? So we may construct the polynomial if we know the zeros, and let's see, we know that we want a third degree polynomial, so we need to have 3 zeros, right? Can anybody tell me what the zeros of this polynomial? We already know 2 zeros. We know 2 plus I, so we know 4 over 3. Let me start like this. We know 4 over 3. We know 2 plus I. What's the other one? Very good. 2 minus I, right? And 2 minus I. And what's the justification of this? Because, well, it's a complex number, right? Since 2 plus I is a 0. We are given the 2 plus I is a 0, so 2 minus I has to be a 0. Everybody okay so far? All right, I will assume that you are okay. So if you have your 3 zeros, then we can write down our polynomial. So so far, our polynomial may look like this. A polynomial could be just x minus 4 over 3 times x minus 2 plus I times x minus 2 minus I. Of course, this is not the answer that we want to give because, first of all, the coefficients have to be integers, so we don't want to have fractions in there, and we don't want to see complex numbers either, okay? So we need to multiply and do stuff in here. Okay, so let's see. The first thing that I'm going to do is I'm going to leave instead of x minus 4 over 3, because after all the information I was given was that 4 over 3 was a 0, right? Instead of x minus 4 over 3, what would be another equivalent factor that we could write that would give me 4 over 3 as a 0, but doesn't use fraction? Can anybody tell me? What would be a factor that we can write that gives me 4 over 3 as a 0, but that doesn't use fractions? What other linear factor give you 4 over 3 as a 0? Do you see it? So the naive thing is to do this, x minus 4 over 3. But we don't want to do that because 4 over 3 is a fraction and we want integer coefficient. So if we start multiplying, we're going to end up with fractions. So we don't want to do that. So how can we avoid this? Very good. 3x minus 4, right? If we write 3x minus 4 instead, this will still give me 4 over 3 as a 0, right? When you solve the equation. But the nice thing about this is that when you multiply, you're going to get integers. You don't get fractions. So instead of 4 over 3, I'm going to go ahead and write here 3x minus 4. Okay? Once again, this will still give me 4 over 3 as a 0, but it has the benefit that it's giving me integers, not fractions. Okay, so now we're going to go ahead and we're going to clean up the other one. So remember, here we have, so x minus 2 plus I, x minus 2 minus I. I'm going to rewrite this as x minus 2 minus I, x minus 2 plus I. So the difference of squares, x minus 2 squared minus I squared. That's going to be x squared minus 4x plus 4 plus 1. So you get x squared minus 4x plus 5. more clear there. So x squared minus 4x plus 5. And then we multiply this, and so we can give polynomial nicely. So let's see, 3x cubed minus 12x squared plus 15x minus 4x squared minus 16x minus 20. So finally, here is a polynomial with integer coefficients. It's combined like terms. Minus 16 squared minus x minus 20. A polynomial with integer coefficients of degree 3 that has the desired properties. Okay, so let me make sure that I did not. So it's positive 15, and is that 16? Oh, 16 is positive. Negative times negative, that's positive. So this will be 31. Okay, plus 31. Okay, there we go. So here is a polynomial of degree 3 that has integer coefficients, and this polynomial is guaranteed to have those 3 zeros that we gave at the beginning. Okay, questions? Any questions on the other example that we did? Okay, good. So let me give you one last theorem, because so far what I've told you doesn't really help you to minimize the least, doesn't help you much to minimize the least that the rational zeros theorem gives you. Okay, and so this theorem that I'm gonna write is called the Descartes rule of sign. Okay, so let me actually go ahead and, to save time, let me bring this up here. How do I do this? I'm not sure I'm saving time with this, but all right. So to save time, let me just copy this theorem here. It should show up now in here. So this one is called the Descartes rule of sign, and basically what this theorem is going to do for us is, this theorem is going to tell us, let's see, it was too big, I think. Let me fix it a little bit. Oh, there we go. Okay, so what this theorem is going to do for us is it's going to tell us among the real zeros, this also includes rational or non-rationals, okay? So among the real zeros of the polynomial, it will tell you up to how many positive zeros you can have and how many negative zeros you can have. And this will be helpful, because if you have a big list, and let's say that you already found 2 positive zeros, and when you do this test, it tells you that you can only have up to 2 positive zeros, you already know for sure that all your other choices, they have to be negative. So you can ignore all the other positive guys. Okay. So in this sense, it kind of helps you sometimes to narrow down your list of zeros more. Okay. So let me explain to you what the Descartes rule of sign is about. Right. Okay, so here you need to understand what we mean by sign change in a polynomial. So I'm going to explain that down here, and then we're going to come back to this theorem. Okay, so let me explain what we mean by change of sign of a polynomial. Okay, so the sign changes in a polynomial is just figuring out how many times the polynomial changes sign when you go from one to another one, looking at the coefficients. So here is an example. So sign changes in a polynomial. So when we do an example, it's more clear than trying to write down formally what this is. So imagine that we have this polynomial, 2 times x to the 6 minus 3x to the 4 minus x cubed plus 5x squared minus 6x minus 4. Okay, so let's figure out how many sign changes do we have here. Well, first of all, you order the polynomial in decreasing order of degrees. okay? And then you start looking at the terms, and then you count every time that the sign changes from one term to the next. For example, here we go from positive to negative, okay? So here we go from positive coefficient to a negative coefficient. That's one sign change. Then it stays negative, so there's no change here. Now here we go from negative to positive. So that's another sign change, and then we immediately go again from positive to negative. And then we stay negative. So here we have a total of 3 sign changes. Let's see, are there any questions on what I mean when I say sign changes? Do you understand how to spot this? All right. Now, what is this doing for us? Why is this helpful? Now, again, this is also a hard theorem to prove, okay? So we're just gonna use it. So there's a theorem which is called the Descartes rule of sign, and here is what it says. Suppose that you have a polynomial with real coefficients, and the important thing here is that it cannot have a zero constant term. So it has to have non-zero constant term. That's important, okay? If it doesn't, then that's not a big deal. You just factor out. That means that everybody has an x, at least. So you factor that out. So you factor that out, you get x equals 0, as you 0, whatever multiplicity it is that you factor out, and then you deal with the polynomial that you have left that has a constant term. So this is not really a restriction. So suppose that you have a polynomial with real coefficients and non-zero constant term, then the number of positive real zero is going to be either the same number of the sign changes of f, or that number minus an even number, okay? So for example, in this case, we had 3 sign changes. So that means that so let's actually use that. So possible positive real zeros are going to be either this number, which is 3, or this number minus an even amount. So in other words, the way you get the possibilities is by doing minus 2, minus 2, minus 2 all the time, right? So 3 is either 3 or 1, and then we stop because it doesn't make sense to say that you have negative 1 positive real zeros. So this polynomial is going to have either 3 or 1 positive real zeros. In particular, it's telling me that it will have a real zero, and it's either 1 or 3. Okay, so this is helpful when you consider the list. And how about the negatives? Well, that's what the second part of the theorem tells you. It says the same statement, but instead of f, you need to plug in negative x. Okay, so for the negative, let's say that this is our f of x. Let's use this as our example. Then you plug in negative x, and remember, what you do is you replace x by negative x. Basically, what this does is the even powers, they remain the same, nothing changes because the even power kills the minus. Odd powers, the minus survives, so you change the sign of the coefficient. So f of negative x, this will be 2x to the 6 minus 3x to the 4, they stay the same. Now the cubic term becomes positive x cubed, the squared term stays, the linear term becomes positive 6x, and then the constant term stays. Okay, and now we repeat the same process. Let's count the number of sign changes that we have here. So here we have 1 sign change from positive to negative, another sign change from negative to positive, and then stay, and then at the end we have another sign change from positive to negative. So how many sign changes did we find here? 3 sign changes. So that means, so what are the possible negative real zeros for this polynomial that we wrote? We either have 3 or 1. So it's always the same thing, either that number or that number minus an even amount. Okay? If you would have had, I don't know, let's say 6 sign changes, then the possibilities would be 6, 4, 2, or maybe 1. Okay? So that's how you write down your list possibilities. Okay, anyways, questions. Do you understand what the statement says? So instead of looking at this big statement, let's look at the example. Probably it's easier to look at the example. Descartes' rule of sign. Do you understand how to apply it? All right, so Then let us do one more example, and then we call it a day. So I'm gonna use let's see, determine the number of positive and negative real zeros. Determine all possibilities, including complex zeros. Yes, and then of course the upshot is to be able to solve, but we're not gonna have time to solve the equation because there are like 3 minutes left. So let us at least figure out all the possibilities. And almost, Sarah, the amount of changes determines the amount of positive zeros or that amount minus an even number. Let's do another example. You're gonna see, and this is about real zeros. Okay, the Carter rule of sign is about real zeros. It never mentions anything about complex zeros. Okay, so if you look at the statement, it never says anything about complex zeros. Statement number 1 is about positive real zeros. Statement number 2 is about negative real zeros. There is nothing about complex zeros. You can deduce some stuff about complex zero by using the knowledge of the other theorems. Anyways, let's do this. So example. So number 3, determine the number. So determine the number of positive and negative real zeros. You know, like the possibilities, and also, so in other words, I want you to find all possibilities. So find all possibilities. There could be different combinations, but this is better than going blindly when you're looking for zeros. Okay, so let me show you what I mean. So for the first one, let's start with degree 4. Let's say 4x to the 5 plus 6x cubed plus 2x squared plus 6. Okay, so here we have this polynomial, and then in this column we're going to write the sign changes. So sign changes. So how many sign changes do we see for f? How many sign changes does the polynomial f has? Anybody? Come on, this is a very easy question. 0 sign changes, right? There is no sign changes. Now we are also interested in f of negative x, so let's do that right off the bat. So these minus survive. So minus 6x cubed, then plus 2x squared plus 6. How many sign changes do we see here? We spot 1 right here, right? So there is 1 sign change. Okay, so we're gonna do this little table in which we're gonna put here the real zeros, and then the real zeros, they are gonna be split into how many positive do we have, how many negative do we have, okay? And then we're gonna have here another column that has to do with the complex zeros. And then it's good to write here the total. So how many zeros are we expecting in total for this problem? How many zeros are we expecting in total? In total, how many zeros in total are we expecting? Look at the degree of the polynomial. The degree of the polynomial is 5, so we are expecting 5 zeros in total. Let's see how we can, distribute these zeros. Let's see, what are the possibilities for positive? Well, there are really no possibilities. So there are 0. We are not going to have any positive real zero. And then if we're going to have real zeros, there is only one possibility, namely 1, because you cannot do minus 1, right? So where are the other 4 zeros? Well, even though the theorem is not telling us, you know this, the other 4 zeros are complex. Okay? So this polynomial, if you want to work with it, you know that it's only going to have 1 real zero. This zero is going to be negative, and the other guys are complex. So good luck. So this would be a hard polynomial to work with. Okay? To find those 4 complex zeros, that would be hard. So let me just do one more and then stop. I know I'm out of time, but I think I did one easy example. Let me do one that's a bit more interesting, and then stop right there. And we're not gonna find the zeros. We'll just practice how to do these distribution of the table so that you can use it at your disposal. So here is, let's work with the degree 7. Okay. So the reason why I wrote it like this is because the first job is to order the polynomial. So order the polynomial. Negative is x to the 7 plus 8x to the 6 plus 3x to the 5th minus x squared minus 3x plus 1. Okay, that's the first thing. Now let us write down the sign changes. Sign changes. So how many sign changes do we have for the function g? Let's see. So here we have 1, then stays, then 2 stays, then 3, right? So we have 3 sign changes. Now let's figure out g of negative x. So odd power, you have to change the sign of the coefficient. Even power stays the same. So how many sign changes do we have this time? Here is 1, here is 2, right? So we have 2 sign changes. Okay, so we are ready to do our little table. So let's see, positive real. How many choices do we have? We either have 3 or 1. Okay, because remember 3 sign changes, but then a minus an even amount, and then negative real. How many choices do we have? We either have 2 or none. All right, so let's do a table. So real zeros, and then this we split it into positive, negative. Then here we have complex zeros, and then it's always good to keep in mind the total. What's the total number of zeros that we are expecting? The total number of zeros is 7. So what that means is that when you do the table, when you add these numbers, when you add the rows, you have the sum has to be equal to the total. Okay. All right. So let's see. For the possibilities, let's first figure out the possibilities. So in the case that you have 3 positive real zero, then you could have 3 positive. Let me use colors here. So you may have 3 positive, but then that could be combined with 2 negative or non-negative. Okay. Then you could also have 1 positive, and then that could be combined with 2 negative or non-negative. Okay. So there are 4 options there. And now in each of these outcomes, let us try to figure out how many complex zeros we're gonna have. Let's say in the first outcome, in the case that we had 3 positive and 2 negative, how many complex zeros are left? 2. Good. In the other outcome, 3 0. How many complex zeros? 4. Good. Then the other one, 4 as well, and the other one, 6. Okay. So again, it doesn't tell you what the zeros are, but at least you have now a picture, a distribution of how the zeros may be arranged. And so, if you're doing your problem and you figure out that there is, that let's say that you already found 2 negative zeros, then you know that don't look for more negative, the rest are going to be positive. And now you have possibility to finding 1 or 3, okay? I don't know, it kind of gives you more perspective. You have a big list, so you can use this wisely to maybe shorten down the list a little bit, okay? So my advice to you is use this wisely. So as you can see, as long as you know the zeros and multiplicity, then we can sketch the graph, regardless of the polynomial. So that's why we're going to spend now our efforts in trying to figure this out. How do we find zeros of polynomials? Okay? And the first moral of the story here is that in general, I want you to understand that this is hard. Okay? So in general, this is very hard. Let me write this down. So remark to graph polynomials. I mean, we already said that above, but anyways, let's stress it again. We need to be able to find the zeros. So we need to be able to find all its zeros. Okay, and in general, this is hard. Of course, sometimes it's easy, like the one just did. We were able to find all the zeros very easily, but in general, this is hard. And let me give you an example of something that actually is impossible to precisely find the zero, okay, or the zeros. So find, and let me say a real zero, because there's another thing. Sometimes the zeros are complex. As you know, if you have, for example, imagine that you have this, the polynomial x squared plus 4. So not an equation, polynomial. This is not going to have, or let's make it even simpler. Let's put a square plus 1. This is not going to have real zeros at all. The two zeros that this one has are complex zeros, plus or minus I. Okay? But well, this is easy. We know how to graph this, so it's not an issue. But even if there are real zeros, sometimes it's very hard. In fact, sometimes it's impossible to find them precisely. So let me show you. So find a real zero of the following: f of x equals, and let's write a seemingly innocent polynomial, x cubed plus x plus 1. So in other words, remember, to find a zero means that you want to figure out a value of x that will make this polynomial equal to 0. So really, the job here is to try to solve the following equation. We would like to solve x cubed plus x plus 1 equals 0, and we want to come up with a real solution, at least, for this. Okay? So, any ideas? How do we find, so, any ideas? Okay, how would you factor this? Ramses and Maria, when you say division, what do you divide by? Divide by what? Something very simple. Well, this is not quadratic, right? This is a cubic. So this is a degree 3. Indeed, if it was degree 2, yeah, we know everything about degree 2. If you have a quadratic polynomial, then you are in luck. You know everything about it. But higher degree, that's a different story. Yeah, exactly. We need to find a factor first. Good. But that's actually the question, right? What's a factor? You know, a factor, that's the same thing as knowing a zero. So how do we find a zero? So that's the first theorem that we're going to write next, the factor theorem, that basically says that if you have a zero, then you have a factor. And if you have a factor, that gives you a zero, of course. So I'm just showing you this just to let you know that, life is not that simple. There are these little problems, and then they immediately become very, hard to solve if you want. But anyways, we're gonna try to come up with a satisfactory solution. So what I'm trying to tell you here is that we cannot hope to be able to find zeros all the time. Of course, the examples that you're gonna be given, those are examples that you can find the zeros. But in general, if you go out there and you find a polynomial, chances are that you will not be able to find the zeros precisely. But still, you should be able to do something, because after all, the computer, if you put this in a computer and it will tell you what the solution is, at least it will approximate the solution with as many accuracy as you want. Okay, and if you're going to be engineers, you have to be able to do these, solve equations like this. Okay, and I'm going to show you a way that actually how the computer will go ahead and tackle this problem. And nowadays they use more advanced algorithms, but there are ways to kind of figure out what sort of zero this function is going to have. Let me show you this. All right, so let us use what we know. Let us use analysis. Let us analyze this. So let me write a little remark. First of all, let us try to see if we can identify what type of zero we are expecting here. In particular, I'm going to appeal to your common sense. Do you think, what can you tell me about the sign of this zero? This number that we're trying to look for, if it exists, actually. Maybe it doesn't exist, right? But what do you think? Okay, so I'm going to tell you different things now. Can you tell me what sign should the zero have? So what I'm saying is will it be positive, will it be negative, or it could be both? What do you think? Okay, good. Why? Why negative? In other words, why cannot be positive? Does everybody see that positive makes no sense to have a positive 0 for this polynomial? If you put a positive number in this equation, the left will just be positive. There's no way you can get 0. So everybody okay with this? You're cubing the number, and then you're adding the number, and then you're doing +1. So whatever it is, you better give me something negative, because if you put something positive, there's no way you're going to get 0. So that's one thing to notice, that if you're looking for a solution, it's going to be a negative number. Okay? So also, I want you to realize that this will have solution, because maybe there are no real solutions. I'm asking you to look for a real 0. Maybe there are none, like x squared plus 1. There are no real zeros there. Okay? So, but I'm claiming that this has a real solution, and the secret is because of the end behavior. So the remark is that this equation has a solution, or a real solution, at least. Okay, has a real solution, and the reason is because of the end behavior. Because f, first of all, we know that f is a continuous function. Remember, every polynomial, the graph of every polynomial is continuous, meaning you can draw it without lifting your pencil. And let's put this with the end behavior of the function. Okay, Maria, so look at the equation. Yes, it's x squared plus x plus 1. We're trying to look for the value of x, so when you plug it in, you get 0. Do you think that x could be positive? What happens if x is positive? What are you going to get on the left? You're going to get a positive number cubed that's still positive. Then you're adding the number itself is still positive, and then plus 1. So you're just getting something positive on the left. So there is no way that you can get 0. So just by looking at that, we can realize that whatever we're looking for, it better be something negative. That's, it's better than not knowing anything. So at least we know that we're expecting something negative. Now, the question is, will there be actually a solution? Well, let's convince ourselves. This equation has a real solution because of the following. First of all, it's continuous, the graph, so you cannot leave the pencil. And we also know the behavior. Let's see. As x approaches negative infinity, what can we say about the function? Who can tell me? What does f of x approaches to when x approaches negative infinity? What can we say about the function? So in other words, what can we say about the end behavior of this function? Who can answer the question? We discussed this last time. Remember, this is a polynomial. Just focus on the leading term. So when x approaches negative infinity, what do we say about f of x? It goes to negative infinity, right? And what happens when x approaches positive infinity? What does f of x approaches to? Positive infinity. Very good, because the leading term is x cubed. So what does that mean? It means that if you're going to graph the function, let me write it somewhere here. If you're going to graph the function, where do we start? In what quadrant do we start? So remember, the quadrants are 1, 2, 3, 4. So what quadrant do we start? We start from quadrant 3, right? We start from down here. We're coming negative. We don't know what's happening in the middle, right? We don't know what's going on in the middle, but where do we finish? In what quadrant do we finish? We finish in quadrant 1, right? So we start from down here, and then we finish up here in quadrant 1. So what happened? We started below the x-axis, and then we finish above the x-axis. And remember, whatever you do when you graph this function, you cannot leave your pencil. So what do you think is going to happen at some point? What are you forced to do? At some point, you're going to be forced to cross the x-axis, right? Because if you start from down here, and you're gonna draw whatever you draw, you have to go through the x-axis, because you cannot leave your pencil if you start in quadrant 3 and you finish in quadrant 1. Does everybody understand this? Because the function begins negative and finishes positive, so it has to become 0 at some point. There is actually a name for this. This is a theorem. This is called the intermediate value theorem. Okay. So the conclusion here is that because of this end behavior, it must cross. So it must cross the x-axis. So that means that it's going to have a solution. There has to be a zero. Our job is to find it. This is called intermediate value theorem. I abbreviate this with IVT. So moreover, we know that this is going to happen for a negative number, right? Moreover, this zero, this x is going to be negative, okay? Moreover, x will have to be less than zero, since otherwise f of x will be positive, okay? And we're not going to have a zero. All right, so let me pause here. Let me write down the intermediate value theorem, and then we're going to come back to this example. So the idea that we just used here was what we call the intermediate value theorem. Again, this is just to convince ourselves that there is a solution. We don't know what it is yet, but at least we know there is something to be found. So intermediate value theorem. That's what IVT stands for. And basically what it says is that if you have a function that's continuous over an interval, okay, over a closed interval, and if at one end of the interval the function is positive and the other end is negative, or the other way around, so if the function changes sign inside that interval, then it has to go to the x-axis, because it's continuous. So when you're drawing it, you're going to leave your pencil, and if you change from positive to negative or from negative to positive, you have to go to zero. You need to go to the x-axis, okay? So that's basically what the intermediate value theorem says. So let f be a continuous function. Be a continuous function. And this is really true on an interval, but if the function is continuous everywhere, like polynomials, then of course it's going to happen on any interval. But I would say continuous on an interval. Let f be a continuous function on an interval AB. In our case, our function is continuous from negative infinity to positive infinity. Okay. So the statement is the following: if f of a, in other words, the value of the function at a, and f of b have different signs. So if the value of the function at the endpoints have different signs, then the conclusion is that f has to have a zero in between, inside that interval. Okay. So have different signs, then f of x has a zero between t to e, between a and b. So what that means is that there is a c with c between a and b, and of course f of c equals c. Okay, so that's what the intermediate value theorem says. Basically, if your function is continuous on an interval and it changes sign at the endpoints of the interval, then inside that interval there has to be a zero for the function, because that means you have to go to the x-axis at some point. Here is a little picture to go with it. So I don't know, let's say that this is a and this is b, and for the sake of argument, let's say that at a the function is positive, and at b, let's say the function is negative. Okay, so we are here and we are here. The function is continuous, so when you're sketching the graph, you have to go through the x-axis. Okay, this will be your c. There is no other choice. Or it could be the other way around. Here is your a, here is your b, and let's say that at a the function is negative, and at b the function is positive. So you begin down here and then you finish up here. Once again, when you're graphing the function, you need to join the dots. You have to go to the x-axis, and you may go more than once. Okay, so notice that you could do this. There are many things that you can do. You can go more than once, but you have to go at least once. Okay, that's what this theorem is telling us. So function is continuous and changes sign on an interval. It has to have a zero inside that interval. Well, we're gonna take advantage of this to try to figure out a solution, or at least an approximation to a solution to our equation. Okay. All right. So let's go back. So before I go back, do you guys understand the statement? Do you understand what the intermediate value theorem is saying? Does this make sense to you? Okay, so let's see if we can use this in a clever way to figure out, what sort of solution we're expecting. So back to our example. Okay, so we have x cubed plus x1 equals 0, right? This is what we wanted to figure out. We already know that whatever x is, it better be negative. So our job, if we want to take advantage of the intermediate value theorem, is let us try to look for two numbers that are negative, a priori, so an interval on the negative side in which the function changes sign, okay? So, you can think about many choices, but let us start with something very easy first. Notice that if you plug in 0 into the function, you're going to get 1, right? Because that's the y-intercept. And if you plug in -1 into the function, what do we get? In other words, remember, this is our function f of x. What's f of -1 and what's f of 0? Who can tell me? What's f of -1 for this function? What happens when you plug in -1? You get -1, good. And what happens when you plug in 0? You get +1. So what do we have? We found ourselves two numbers, and at one point is negative, at the other point is positive. So you can think of this as being your interval AB in the theorem. So we know that the function at -1 is negative, +1 at 0 is positive, sorry. So what does that mean? By the intermediate value theorem, what do we know? There has to be a 0 in between, right? So by intermediate value theorem, f has a 0, which is c, which is between -1 and 0. In other words, this c that we're looking for, okay, so that means that this c that we're looking for, which will be the solution to our equation, okay, let me call it x, as 0, x equals c, in which c is going to be between -1 and 0. So that means the x that we're looking for is really -0 point something. At least that's that's a good clue, because at least we don't have to go too far away to look for this guy. Do you understand this so far? Okay, so again, let me draw you a picture. So what happened was, here we have the x and y. So here is 0, here is -1, and what we figured out is that at -1, the function equals -1. So our graph, whatever it is, it has to go to this point, and then at 0, it was equal to 1. So it was up here. So what we figured out is that when you're drawing, you have to go through the x-axis within this interval. So the point that we're looking for is somewhere in here. Yes? So now what is the next thing that we would like to know? I mean, there are still a lot of possibilities. So now what we're going to do is try to figure out one decimal place at a time for this, okay? And I'm going to do like 2 decimals, and then, you will see that you can keep on doing the process that I'm about to do until you are satisfied with the accuracy that you want, okay? So now, of course, I'm going to use a calculator, because like I said, this is something that a computer would do, because in this case, we cannot do this by hand all the time. Like, we cannot find the exact solution. The computer cannot find the exact solution either, but we can do it very fast with a calculator. So I'm going to be using Excel for this. But let me explain what's the idea. The idea is exactly what we just used. We keep on using intermediate value theorem. So what do? We figured out that at -1, the function is negative. At 0, the function was positive. So whatever we're looking for is between those two numbers. So it's -0 point something. Okay, now I want to close on it a little bit more. So here is what we can do. So if some of you know a little bit about programming, computer science, there is something that's called divide and conquer. Okay, actually that's not just computer science. In the art of war, this is also used, right? So anyways, one thing that you can do is, let's say that you're looking for an object, right? What you can do is you can split the set that you are dealing with, you can split it in half, And then you can look for the object here. If it's not there, you already know that it's in this piece. And then you continue. You split this in half, and then if it's not here, you know it's here. And that way you're getting closer and closer into where the object could be. Instead of dividing by half, since I'm gonna be using a calculator, then it's easier to just divide by 10, okay? But I guess, let me show you first what was the idea. If here is -1 and 0, I divide this by half, that means this is -1/2, right? Or -0.5. What I'm gonna do is the following, but then we're gonna do it more quicker, okay? But this is the idea. You plug in -1, we already know what it is. The value of the function at -1 equals -1. The value of the function at 0, we know what it is, equals 1. Now we're gonna figure out what's the value of the function at -0.5. So we plug in, -0.5 into the function. Let me do this quick. So -0.5, then we need to cube this. Then we do -0.5, then we add 1. Okay, so I'm getting 0.375. Okay, so what do we get from here? Let's see. I think hold on, let me do this again. Not sure. So 0.5 negative, let me cubic. Then -0.5, and then I'm gonna do +1. Yeah, I get 0.375. So what are we getting here? We're getting a positive number. Yes. So what does that mean? When we look at this, where do you think the 0 that we're looking for is? So 0.375, this is positive, right? And then we had that this guy was negative. So where is really that 0? Is somewhere in here. Because again, the function is positive here, the function was negative here, so we have to go to the x-axis somewhere in here. So we know that what we're looking for is the -0 point something. That something is a number between 9 and 5. Yes, it's -0 point something, but it's not going to be on this half, but it's on this one. Do you understand this? All right, and the idea is that, normally you would just keep on doing this. Now you do half, etc. What I'm gonna do is, to be able to obtain the first decimal place in one shot, I'm gonna split the interval into 10 pieces, okay? And then we're gonna figure out the value. We plug in all those points into the function, and then we try to see where the change of sign happens. Now, this is gonna be very painful to do it by hand, so that's why I'm gonna be using a calculator for that. I'm not a calculator, but I'm gonna use Excel. Excel is perfect for this. Okay. So let's see. Let me share my screen. Another screen. Let me open up Excel. And again, I'm taking this time just first of all to show you, because in practice, if a polynomial comes your way and you want to figure out a 0, you need to understand that it may not be possible for you to find it exactly, but maybe you can approximate it, and you can always use what I'm doing right now. Okay. Okay. So let's see. Can you see my screen? Make sure that you can see it. Okay. So let me make it bigger. Can go with 200. Hopefully it will be enough. Okay, so I'm gonna do a little table of values. So here we have, I'm gonna be putting x in here, and then let's see. Okay, let's work like this, and then I'm gonna have here the values of the function f of x. Okay, now f of x, remember, it was x cubed plus x plus 1. It's a function. Okay, should I make it bigger, or that's fine? Is the size okay? Let me make it a little bit bigger. Maybe 250. Oh, that looks better. Okay, and then let's put our interval here. So remember, we're in at 0, or actually, so 0, and then I'm gonna do -0.1. I'm splitting into 10 pieces. So negative 0.2, and then all the way up to negative 1. Okay, so all right, so we will see. So we have this. Remember, we want to keep on getting more accuracy. We want to keep on getting more accuracy. Okay. Okay. So this is our interval. We split the interval into 10 pieces, and now let us evaluate the function. And let's see. So that's gonna be x cubed. Oops. So x cubed plus x plus 1. The value is 1 at 0, as we know, and then we just drag and drop. Okay, so let us take a look at the y values, which is this column over here, and let's try to figure out what's going on. Let's see. What is it that we need to be looking for? We need to be looking for a change in sign, right? Because that's when it's going to go from positive to or from negative to positive. And if you look at it closely, we realize that that change in sign happened right here, right? So at negative 0.7, it was negative, and then at negative 0.6, it became positive. So right here, we see a change in sign. Everybody see that? So what is that telling us about our 0? What's the first decimal place of our 0? So let me go back. I have to be going back and forth. So with this information that we have here, so what do we know about this so far? So let me copy and paste this. So here, okay, so it should show up. Okay, so from this information so far, what we get is that from here it follows that this x that we're looking for, right, is going to be bigger than negative 0.7, but is less than negative 0.6. So that means that x is going to be equal to, equal to negative 0.6, something. At least we know better than before. At least we know now that it's going to be negative 0.6 something. Everybody okay with this so far? All right. So now let's say that you wanted to, 2 decimal places of accuracy. Let's say that you're not happy with this, that you would like to know what goes in here, the second decimal place. Well, let's do the process again. So we're going to keep that interval. We're going to pick that interval, the one that begins at negative 0.7 and finish at negative 0.6, split it into 10 pieces. 2, 3, 4, 5, 6, 7, 8. I think one more. 9. Okay, I should do one more. Okay, split into 10 pieces, and again, plug in your points and then figure out whether there is a change on sign. So I'm gonna do it once more and then I'll stop with this. Okay, so let's go back here. So this is there a question? I cannot see his chat now. Okay, y between negative 0.7 and negative 0.6. Okay, Anton. So remember, what's this column right here? This column right here are the values of the function for the given x value that we have in this column. You okay with this so far? Okay, let us look at this. And when we look at the values, we see that the first time that the function jumps sign from negative to positive is right here, right? Here we see a change in sign. Here we see negative, here we see positive. What does that mean when we read this table? This is telling me that if I plug in negative 0.7, we get a negative number for y. Yes? And if we plug in negative 0.6, we get a positive number for y. So what does that mean? it means that the function is changing sign on this interval between negative 0.7 and negative 0.6. Do you understand this? So then that means that there has to be a 0 between these two numbers, right? That whatever it is that we are going through the x-axis is between negative 0.7 and negative 0.6. So that's how we know that. Are we good? All right. So now let us try to see if we can figure out what that is, okay? So we want to now take that interval and, play the same game. Now I'm going to begin, instead of 0, I'm going to begin at negative 0.6, and I want to finish at negative 0.7. And let's split this. So this will be negative 0.61, negative 0.62, and so on and so forth, right? This way, we're going to be able to figure out what is the second decimal place. All right. And since we already had the formula written down, then notice how it automatically calculated for us. So let's see, who can tell me who can tell me in between what is a 0, between what and what? Very good, between 0.68 and 0.69. In other words, if you spot here, you will be able to see the change in sign, right? So now we know that whatever it is that we're looking for is in the two numbers, okay? So let's go ahead and copy this, paste it here, do it once more. Now we check the other one. Okay. So be patient because I'm using two computers. And I have to switch from one to the other one. Okay. So now that we know that the 0 was between negative 0.7 and negative 0.6, we did the calculation again, and then we figured out here is where the change in sign is happening. Now it turns out that it's going to be between negative 0.69, okay, and negative 0.68. So what is this telling us? This is telling us that x is going to be equal to negative 0.68 and so on, okay? And as you can see, we're getting closer and closer to what the solution should be. If you want to know more decimal places, now you understand what to do, right? You take this interval again, negative 0.69, negative 0.68, split it into 10 pieces and keep on doing this process until you're satisfied. Okay? All right.